Welcome to Module 7 of our electrical grid testing and commissioning training series, focused on capacitor banks. In this session, we'll dive into everything you need to know about testing and commissioning these vital components in the electrical grid. Let's get started on building your expertise for 2026 and beyond. Here we have the reference framework for testing and commissioning electrical grids. This slide lists key organizations and standards that serve as authoritative sources for commissioning manuals and test scripts. Some of the most recognized references include IEC, which stands for the International Electrotechnical Commission, and IEEE, the Institute of Electrical and Electronics Engineers. Other important bodies are ASTM, known for testing materials, NEMA, the National Electrical Manufacturers Association, and ANSI, the American National Standards Institute. Additionally, we have CIGER, the International Council on Large Electric Systems, ICA focused on insulated cable engineering, and KEMA, an electrical engineering verification body. A crucial governance rule to remember is that when there's any conflict between project specifications, manufacturer instructions, and standards, we always apply the most stringent approved requirement. It's also important to document which reference was used on the test sheet to ensure transparency and traceability for future reviews. Here we have the first part of capacitor bank testing and commissioning, focusing on the essential procedures needed to ensure proper function within the electrical grid. This slide presents a reference schematic that guides us through visual inspections and several critical tests, including insulation resistance, tuning-reactor inductance, tan delta, as well as capacitance and internal resistance checks. Each of these steps is vital to verify the integrity and performance of the capacitor bank before it goes online. Following the guidelines in Commissioning Manual Number 7 to 1.1 helps maintain consistency and reliability throughout the process. Here we have a detailed overview of the capacitor bank testing and commissioning process. The focus here is on inspection, insulation, inductance, tan delta, and capacitance checks, which are critical to ensure the system's reliability and safety before energization. We start by verifying all pre-energization conditions, including insulation integrity and tuning-reactor inductance, along with dissipation factor and capacitance balance. These steps ensure the equipment is ready and safe for operation. The references listed guide us throughout the procedure, including project commissioning procedures, approved drawings, and manufacturer instructions, ensuring compliance with standards. The required instruments include power factor and tan delta test instruments, insulation resistance testers, digital multimeters, and other safety equipment such as discharge sticks and personal protective equipment. The testing script breaks down into clear steps. First, we review all documentation, permits, and ensure the capacitor bank is properly isolated and discharged. Next, we secure the work area with barricades and safety tags and confirm that all personnel understand the test boundaries and hazards. Mechanical inspections follow, checking structural elements, insulators, bushings, and connections for any issues. Then, insulation resistance measurements are taken on all units and phases, with safe discharge after each test to prevent hazards. We measure tuning-reactor inductance and compare results with approved design tolerances to detect deviations. The dissipation factor or tan delta is also measured to assess insulation condition, recording voltage, current, capacitance, and losses carefully. Internal resistance and capacitance readings help identify any imbalances or damaged components, and we confirm that residual voltage and unbalance-relay circuits are properly connected and labeled ahead of energization. Acceptance criteria emphasize compliance with project and manufacturer limits, requiring no damaged units, abnormal losses, loose connections, or unsafe grounding before energization. Residual voltage must be verified and within limits before moving ahead. The final package includes all inspection checklists, test results, calibration certificates, photos, and punch list documentation, coupled with client or commissioning witness approval. This hold point confirms safe discharge, acceptance of results, and readiness to proceed with neutral-unbalance and energization testing, ensuring the capacitor bank is in optimal condition to operate safely and reliably. Here we have the schematic for the capacitor bank neutral-unbalance test, an essential part of the testing and commissioning process for electrical grids. This diagram serves as a reference for performing three-phase energization, ensuring the system is correctly powered up. It also guides us through checking residual voltages, which helps identify any lingering imbalances. Most importantly, it shows how to verify the neutral unbalance current and monitor the relay response to confirm the system's protection mechanisms are functioning properly. This step is critical to maintain grid stability and prevent potential faults during operation. Now we are focusing on the capacitor-bank neutral-unbalance current test script, Part 2, which is crucial in testing and commissioning the electrical grid. The main goal here is to ensure the capacitor bank's balanced response. Check the residual voltage condition. Verify the neutral CT path, confirm unbalance protection relay functionality, and guarantee safe restoration after testing. We start by confirming that all preceding inspections and measurements are accepted, and that every capacitor unit is safely discharged before connecting any test equipment. Then we review the unbalance relay settings, the logic for residual voltage relay, neutral CT wiring, voltage transformer references, phase identification, and the approved on-load test method. Next, it's essential to connect the three-phase AC source and all measuring instruments exactly as shown in the schematic. We energize the system under controlled conditions while continuously monitoring phase voltage, phase current, neutral unbalance current, and relay status. The balance bank condition requires that the neutral unbalance current is 0 or within the approved tolerance. If permitted, simulate an imbalance or perform a relay functional test to verify the alarm and trip mechanisms without causing damage. Residual voltage must be recorded and should not exceed 10% of the rated voltage before energization during on-load testing. After testing, the system should be carefully de-energized, discharged, grounded, and restored to normal connections, confirming that relay, panel, and SCADA statuses are all proper before final release. The acceptance criteria demand that neutral unbalance current stays within approved limits, residual voltage is within safe bounds, and the relay behavior matches approved protection logic with no issues like overheating or loose connections. The results package will include all test records, readings, relay event evidence, calibration certificates, and witness sign-off. Finally, the hold point requires operations and commissioning witnesses to confirm no abnormal unbalance exists. Residual voltage limits are met, the relay is restored, and the capacitor bank is safe for normal service. This comprehensive approach ensures the capacitor bank operates reliably and safely within the grid.